the embedding release problem. Let me explain that in the context of collaborative learning. So looking at the current scheme of techniques for privatizing machine learning models, so for the release of a model, or like the model weights, in the context of, say, distributed or collaborative learning, like, for example, like in federated learning, there's been, and with privacy guarantees, there's been like different ways of perturbing the part of the training process so that the resulting model has differential privacy guarantees. And the perturbations have been tried at different parts of the whole pipeline, and the ones that stuck more the test of time have been the ones that focused on gradient perturbation. So how are gradients perturbed during the learning and specifically the optimization process of learning a model? So this is great. I mean, there's certainly a lot of progress in that area. One part of privatization in this setup that has been somewhat understudied relative to the huge body of work you saw with model release is the question of privacy for embeddings or representations at different layers of the model. There's a reason why this is understudied, because if you think about the weights of a model, they are a statistical estimator. But if you think of the representations, these are one-to-one functions, so it's more like a local privacy kind of problem. So it doesn't seem like the obvious thing to privatize first if you want to have high utility in the distributed setting. So the approach we take, that said, there is benefit to privatizing, figuring out mechanisms that privatize embeddings or representations of different layers of a model. But what are the benefits if one could privatize? What are the benefits? There have been, again, somewhat understudied schemes of collaborative learning, which is based on representation sharing as opposed to weight sharing, which is very popular in federated learning. So these methods have, or different variants of these methods or designs have benefits in terms of higher resource efficiency for the client. It also helps purposes like personalization that people have been talking about and so on and so forth. So this is more resource efficient. So the focus of this work that we call power learning is some sort of a modification to the distributed training regime, the design or the protocol of distributed training, as well as privacy guarantees at the embedding layer. So let me just explain the systems interactions involved first before we go to the details of the method. So the system interactions, assume there's a hospital, which is a client, which is resource constrained, and assume a large pharma company, which is not as resource constrained, and they would like to collaborate to train a large machine learning model. So the different components of the hospital's model involve a piece of the privatization network, or the privatization piece. And the client in this paradigm would also have some sort of a surrogate model, which it could use to somehow steer the model towards a reasonable utility. And then the pharma company receives private embeddings instead. This is the representations, which are privatized through the power mechanism. And the pharma company then continues its large model training and so on and so forth to get the final utility of its maybe like a task for treatment plan design or whatever its pharma task is, the ML task. So some more takeaways before we go into the details of how we privatize it are as follows. So this is more in line with what happens in personalization, right? So if you could privatize in this setup, you would only have to privatize once and do like a one round of lightweight communication. And then, so it's not collaborative at every epoch or at every round. So you just privatize and release the embeddings. This is more in line with, say, some notion of personalization or like the large language model or like the BERT embeddings. It's like an embedding release problem. The other takeaways are, of course, we are trying to give formal privacy guarantees. The utility, we don't have guarantees. We show that empirically. There's two other takeaways, which is more, this is a good context to discuss here because there's been some very nice discussions around incentives in markets and data valuation and so forth. So one question that remains there is, what is a utility function that you could design for a data valuation scheme where the utility function depends on privacy? What is the notion of utility in terms of privacy? What does it mean for a record to be easy to be privatized or hard to be privatized? And how would you value this and give costs and disperse payments accordingly? So we get some benefit of that, and we also show that in this kind of a scheme, we could do few-shot learning, which is we can try to identify those specific records in your data set which are easier to privatize at a high level of privacy, and then you can only use those records and not use the rest of the records for training. So it kind of enables few-shot private learning. Okay, so now comes the question. What is happening in the privatization network? Because the rest of it is more like standard ML. Is there some notion of a privacy loss, and how does the training need to be done so that you can guarantee and calibrate privacy levels? So we go back to like the simplest network ever we could do, and then we kind of stitch it into more modern ML. So the simplest network one could think about is the equation you see on the top. So given your data set, this is if you can learn an operator H on your data set, and then if you do a power, hence the name power learning, if you do a power of the operator is a matrix, so you do a power of that matrix, and then hit it to your data set, and then you get the output Z. Now comes a question. So this is like a simpler than a linear neural network, because this is like a trivial network where all the networks have the same weight, and you're just hitting by P. There's no activation, nothing. The H could be a nonlinear function that's set of X, although the operation is being applied in a linear way. So now the question is, how is this operator H supposed to be designed? What are those properties? And what is the power P supposed to be so that we can guarantee privacy, or differential privacy? Secondly, since this is way too simple a projection operation, we then plug it into more of a ML kind of a setup where now we have a privacy network, which is a standard deep network that learns representations. The output of the representation is on which the power operation is applied. So you take the output of your representation, and then you do the power operation. But that said, differential privacy has a post-processing property, but it's not immune to pre-processing. So we cannot just start with the output and assume you'd have privacy guarantees for your input. So we have to figure out how we design the weights of this privatization network, and then get the representation, and then pass it through the power mechanism, and then you have a privacy guarantee. So how is this put together? So the motivation comes from a classical principle in analysis, or like in probability, which is the notion of learning transformations. If you knew the PDF of your data, this is called the change of variable theorem, and when you apply it to like densities, it's called the change of variable theorem applied to probability distributions. So if you had a distribution for your raw data that exists, and you apply some transformations, the question is, what is the PDF after the transformation? That's what the change of variable theorem deals with. Why is this kind of a nice starting point before we do the rest of the math? Because the differential privacy definition is defined on probability distribution. So we need to work on probability spaces in addition to the transformations that we have, so that we can say something about how should the transformation be designed so that you end up with a privacy guarantee. So this is a kind of a visual, right? So it's of course univariate. So if you had a blue distribution that exists, whether you know what the distribution is, what it is or not, and if you apply, say, the exponential transformation, then you get this new distribution that you get through the change of variable theorem, for example. You can have a version, well, it's hard to play this now, but you can have a version of this in, again, in classical distribution theory, on like going from a uniform distribution to a Gaussian, for example. This is a multivariate, but in the 2D case, there's a very popular transformation called the Box-Miller transformation. So this is another application of, for example, the change of variable theorem. Okay, so what is differential privacy? Quick one version of there are many equivalent definitions. One version is if you had two neighboring data sets, the notion of neighborhood is up to your design. One possible notion of neighborhood has been the Hamming distance, but if you generalize the metric to something else, it's called metric differential privacy. So if you have neighboring data sets and you apply a query F and a query M, and then you look at the probability distribution of the output of your queries applied in the neighboring data set, and if those don't change beyond up to an epsilon, bar epsilon, this is called pure differential privacy, and you can have like a slack parameter, which is an additive probability under which the DP guarantee does not hold, and that's called approximate differential privacy. That's epsilon delta. And there are many more variants. As you see, all of these are defined in terms of probability distributions. Hence, the change of variable theorem and transformations are useful. There are also, there's a quick slide on different equivalent definitions of differential privacy. So you saw so if you just do, if you rearrange your definition of differential privacy, you can get a real-life instantiation of this random variable of how the loss behaves. And since we are guaranteeing DP with respect to some sort of epsilon parameter, this random variable, this random variable would always, if the probability distribution of that random variable would always be bounded between plus or minus epsilon. So this is the privacy loss distribution kind of an instantiation of what DP is. This has very nice properties why people working with PLDs, the privacy loss distributions. You can sample from PLD, and then the question is now if you have composition of transformations. People want to know how their privacy budget epsilon is depleting or not depleting and so on and so forth. And they don't want to be too conservative, because if you're too conservative, then you're losing more utility. You want to be as less conservative as possible. So that's where people went from classical DP to newer DP mechanisms like Renyi DP and zero concentrated DP and FDP and so on and so forth. So how is composition being done in a more accurate way when you're able to use privacy loss distributions? The beauty is follows. So if you have the privacy loss distribution for the individual components of the composition, and if you want to get the privacy loss distribution after the composition, all you need to do is a convolution operation of the PLDs. So you want to understand the PLD of a composition, you do convolution of PLDs. Convolution of privacy loss distributions is a lot easier to do computationally, because for any distribution, you need to just sample from individual distributions and add those samples. That is equivalent to a convolution operation. So this is very easy. So you can sample from individual PLDs, add them up, you get a convolution, you get the PLD finally. And this kind of a thing has led to newer versions of differential privacy, like Renyi DP or differential privacy equivalence in terms of information theoretic divergences. DP is equivalent to this hockey stick divergence being less than or equal to delta, where the hockey stick divergence is specified based on the epsilon. There's a hypothesis testing notion of differential privacy, which is an equivalent definition, which says if you run a hypothesis test in terms of an attack where the attacker is trying to guess whether a specific record is in the distribution or not, then you have a type 1 and type 2 error of the attacker's hypothesis test. So there's an equivalent definition of DP, and you see the epsilon and delta plugging in. And you can have different trade-off functions of the type 1 and type 2 error, and then you have a trade-off F differential privacy based on your choice of trade-off. OK, so that's that. So now we've seen that everything is about distributions, as far as if you want to go towards DP. So we are talking about transformations. Now the question is, and we are also talking about the fact that you can generalize the neighborhood around the choice of neighborhood between your data sets to a different metric, which is called metric DP. And there is a notion of equivalent metric DP called Lipschitz privacy, which says that if you minimize the norm of the gradient or the log of the probability distribution of your query to be, if you bound it to be less than or equal to an epsilon, that's an equivalent notion of DP. It's called Lipschitz privacy. And this is these are both equivalent, so this is more computationally wieldy, because that's just a definition, but this is something you can plug into your optimization schemes and so on and so forth, the second equation. So now, how do we do this in terms of a neural network? So we've connected DP with transformations and change of variable theorems in the outputs. So we derive that in order to learn for the power query, in order to learn the condition required so that upon applying the change of variable theorem, the output distribution satisfies the Lipschitz privacy guarantee that I showed you in the previous slide. That boils down to this specific loss that needs to be achieved, which is we call the loss required for privacy. It depends on a few things. One is the Jacobian of your transformation. So it could be the initial neural network and then the power mechanism after that. If that needs to be under control with respect to epsilon. The F functions are basically nothing to do with your transformation. They're just a notion of how hard or difficult it is to privatize. It's basically saying, these are basically the densities of your raw data itself, the density of your data and your density derivative. So if you bound that to be less than epsilon, then you have Lipschitz privacy, and then we are set. We have the benefits of collaborative learning with privacy guarantees with embedding release. But of course, to make it more exact and quantify the uncertainty, because DP is a probabilistic notion, we are having some density estimation terms that we're dealing with. So we do a density estimation and apply the confidence intervals, and we get an updated calibrated epsilon, which is the final epsilon we have. So that's the power mechanism. And now I'd like to conclude by just showing a couple slides on results. So this is one example in terms of the benefit from understanding the cost of privacy, which is if I apply the privacy-preserving loss that I've derived that guarantees privacy on the embeddings, and I shoot for some epsilon that I'm asking for. But then this is a neural network. There's a lot of optimization going on. It's not going to guarantee that you would get the same privacy level for all of your records. So what we get now is a histogram of different privacy levels that one could, at an instance, could have guaranteed after the fact, at post hoc, after running the power mechanism. And then, as you see, if it was very left skewed, it would mean that you can guarantee high privacy for most of your records. If the result happens to be more right skewed, it means you can guarantee not that high privacy for most of the records. So left skewed is better. But now if you have a specific privacy level, I don't want to break your privacy requirement. So if, say, your privacy level is 1, then I can, or 0.5, I can say you only need to use these set of records to the left of 0.5, and so that's a notion of cost or utility of privacy that one can plug in. It is an intrinsic cost that can plug in and say how hard it is or not hard it is to privatize any specific record. And you can plug in into like, your data valuation and market kind of schemes if you need a utility function for privacy. OK, and the final plot. So what happens to the accuracy privacy trade-off with respect to DPSGD, for example? So this is a tabular data set for like a churn prediction. We also done it for like forest fire data set. So the story is the utility privacy trade-off is kind of comparable with respect to DPSGD style techniques. The bottom is DPSGD, above is the power mechanism for embedding release. But then if it is comparable, where is the gain? Apart from the cost or utility function of privacy, the other gain is in terms of the fact that now we are able to do distributed learning with clients having just the personalization piece. So you're going to gain in like a lot of communication rounds not being required. You're getting one-shot release. You're getting you're able to deal with more resource constrained client devices because now you can just have 3 layers on the client and everything else on the pharma company or like the server. So you get that kind of a benefit it's from a distributed piece. OK. Yeah, so closing slide. There's a new reps going on, but I was more excited to be here. So this is an advertisement for our NeurIPS paper, the main conference. There's not been much work done on DP guarantees for inference, and there's a reason why as well, because there was an impossibility theorem of instance encoding that was shared. So we generalize that problem into a metric DP setting, and we give an early mechanism for post hoc privacy for any informally trained network. You plug it into our mechanism, into our post hoc mechanism, and then you make it a privatized piece. So you can have like embeddings released with privacy guarantees, even if your embeddings were not designed with DP in place. You just do standard optimization. You have a non-private model. How do you make it private during the inference? So that's our post hoc privacy paper at NeurIPS. We'll talk about NeurIPS paper here as well. All right, thank you.
Any questions?
When it comes to data variation and differential privacy, isn't there like a fundamental conflict of having a very clear value, like assuming a data set D and one data point stands out in its variation, and assume it's a medical data set, wouldn't that inflict a privacy concern?
So that's exactly what's going to show up in the histogram. Yeah. It's going to say that specific record is maybe not easier to privatize because it's already a very skewed record. So it'll be, if you're going to push it to a lower epsilon, it's going to start trying to be farther from the lower epsilon, unless you really push it hard because you have a very good optimization scheme or guarantee. And it shows up that it is already a costly piece. So the utility function is at least measuring and telling you how difficult it is to privatize or how precious that record is from being very different than the rest of the thing. Secondly, we did a theoretical paper on that does a connection between social choice theory and like voting functions and differential privacy. So everyone talks about the utility privacy trade-off, right? But there's never been a trade-off that's been studied between the welfare of a collaborative mechanism, like a social choice mechanism, or like the influence of any given voter in a social choice mechanism. So we show a trade-off between privacy level epsilon and influence and welfare. But that's, again, like more like starting point work, although it's very theoretical. But the histogram is more practical because you have it computationally with you. Yeah, those are 2 things I can think of.
So another question, have you tried to train a generative model that generates these embeddings with differential privacy and compare that to your approach?
Oh, that's a nice application. We've not tried that. Do you see, are you seeing the benefit of being able to do that from being able, because it's going to be more distributed and client resource efficient generative model, or where do you think the benefit of generative model? over this?
Possibly pre-training the model on public data,
Yeah.
leveraging a lot of the things that you know of from the world, and then fine-tuning on the types of embeddings that you want on a population would help you in that sense.
Right. So I agree because of the benefit of public pre-training and private fine-tuning, which is, we've done that for a simpler problem, which is a predecessor to what I shared, which is if you're doing t-SNE or UMAP kind of a visualization, which is basically a query applied in the last layer of the network, and you just want to know how to do t-SNE or UMAP with DP. We've done that problem, and we've used the private-public kind of a setup, and that's when we see like better gains in the utility for obvious reasons. But it's, yeah, I mean, I can see the value of what you're saying for more traditional ML like this.
Let's thank Praneeth. So that's the conclusion of the morning.